The imperative to achieve net zero emissions by mid-century presents a huge challenge to not only us as a society, but also to industry. Now, while the rapid deployment of renewable energy sources is absolutely fundamental, additional measures are also needed to reach our climate targets, especially when it comes to decarbonising the hard-to-abate sectors. Now, in our earlier episodes, we have discussed how delivering secure, sustainable and affordable energy for everyone is key to a successful energy transition. And carbon capture and storage, or CCS, also plays a vital role in this, particularly for managing the carbon emissions from hydrocarbon-based energy sources and industrial processes while shifting towards more sustainable power. But what is CCS, and why are additional measures beyond the deployment of renewable energy sources actually needed? How can carbon capture and storage contribute to managing emissions from industrial processes during the transition to more sustainable power? And what role do technology innovations like digital twins play in the scaling up of CCS? We will be tackling all of this and much more as we pose the question, how can CCS help speed up the clean energy transition? I'm Fran Scott, and this is the Process Automation Podcast from ABB. We are going to be joined by Nigel Greatorex, the Global Industry Business Manager of CCS at ABB, and Anjani Kumar, Vice President of CoFlow and Professional Services at CMG. But up first is Dr. Colin Hale, Senior Teaching Fellow in Chemical Engineering at Imperial College London, where he leads initiatives at the college's carbon capture pilot plant.
So CCS, or actually more properly CCUS, stands for Carbon Capture, Utilization and Storage. It's a suite of technologies to enable us to achieve our net zero goals by capturing carbon dioxide before it goes into the atmosphere. And then with that captured carbon dioxide, either using it for other things or storing it in existing reservoir formation.
And why is it important for our net zero goals?
In terms of to achieve our net zero goals, actually we're talking about very large numbers in terms of emissions. So there's not really a single technology that enables us to do that. It needs to be a mix of technologies. Renewable energy's got a massive part to play. Being more sustainable in the way we do things has got a big part to play. But actually, if you look at big industrial processes that generate lots of the products that we use day to day, so I mean things like cement production, steel production, chemical processes, food production on a commercial industrial scale, even waste to heat production, they're very, very difficult to decarbonize using just renewables or some of the other resources. This is where carbon capture has a key role to play in helping us to achieve those ambitions.
Absolutely. Now, when it comes to carbon capture, the science has been around for a long time, and yet the technology and the industry is relatively new. Currently, what are the more effective technologies that exist when it comes to carbon capture?
Okay, so in terms of carbon capture processes, I mean, the basic technology is very straightforward, really. We're taking advantage of the properties of carbon dioxide and using those properties to enable us to catch it from a mix of other gases. The basic technology for doing this is really an acid-alkaline type reaction. So that technology has been around for quite some time. For example, for the upstream oil and gas sector, there's what we call gas sweetening processes, which have been used to do similar things to remove acidic gases. In terms of for carbon capture in particular, that's a slightly more newer technology. It's a different application. The original technology was patented around 1930, actually. But it's around the scale for these sorts of processes. It's much bigger scale than previously. And in terms of the specifics for capturing the carbon dioxide, the way that we can do that are using solutions, so liquids, typically amine-based liquids, which react with the carbon dioxide to remove it from a mix of other gases. So that's one technology. That's probably the most common technology that tends to get deployed in things like post-combustion capture processes, or even some of the pre-combustion capture processes. There are solid materials that we can use to capture carbon dioxide, but they're not so effective on a large scale for capturing the amounts of carbon dioxide we're looking to capture. For some applications, there are membrane-based technologies to enable us to do similar things. But again, that tends to be for more niche type applications. Probably the one that's most widely used are amine-based solutions, amine-based solvents.
And when you say amine-based solvents or solutions, my brain is telling me that's NH3. Or could you explain what amine-based solutions mean?
Okay, so in terms of those bits, they've got an NH3 functional group on that reacts with the carbon dioxide in the same way as something like sodium hydroxide would. So it's an acid alkaline reaction. The advantage of using amine-based solutions, though, is that the reaction, instead of just going in one direction, is reversible. So by changing the temperature conditions of the process, we can capture carbon dioxide in one location on that process at a lower temperature, and then transfer our liquid to another location on the same process that runs at a higher temperature to release that carbon dioxide in a controlled way so we can do other things with it, such as utilize it or store it. The solution, the liquid, we can then cool back down and use again. So actually we circulate a solution in a big figure-of-8 loop between those two locations. That means we can use it multiple times.
That's brilliant. I never thought of carbon capture in that way, of having this, I suppose, vector in terms of with the NH group, these amine solutions, just chemically they can bond with, or at least extract the CO2, take it to where it needs to go, in essence, get rid of it, and then you're recycling that amine solution back to pick up more from the gases that are being emitted. That's genius.
So, I mean, that's the main reason that type of solution has been adopted predominantly for these processes, because it means we're not shifting the problem elsewhere. We're not generating lots of additional waste. We can reuse the existing resources in as an efficient a way as possible.
Brilliant. Now, when it does come to carbon capture, what are some of the biggest challenges that need to be addressed?
Okay, so I mean, in terms of one of the key challenges for these sorts of processes, it's really about the scale up, because we're looking at capturing 1 million tons per year of carbon dioxide or more from many of the industrial processes we're looking at. The technology itself is well established, but in terms of that scale, there's engineering challenges associated with making it on a much bigger scale, and particularly in terms of ensuring that those processes are as efficient as possible from an operational perspective, because that can affect things like operating costs, for example.
Yeah, because I suppose as well, there's also a carbon cost of capturing carbon. So you have to make sure that when you look at it as a whole, that the net carbon taken or emitted is actually environmentally favourable.
So in terms of the process itself, the way that it works is we circulate a solution in a big figure-of-8 loop between two locations, one at a lower temperature, one at a higher temperature. We're taking advantage of that figure-of-8 loop to recover as much heat energy as we can. But nonetheless, there's still going to be an additional input of energy that's required to take us from a lower temperature solution that's containing carbon dioxide to the temperature that we need to take the solution to enable us to release carbon dioxide in a controlled way. That additional part of the heating can affect the operating costs of the process. And of course, depending on the way that that energy is generated, that can affect the carbon footprint for these specific processes as well.
And how quick are industries to adapt carbon capture? Are they ready to take it on, or are you feeling some resistance within the industry?
I think in terms of the uptake rate, probably if I would have been asked a similar question about how quickly is this taken off 5 years ago, I would have been a little bit more pessimistic than now, because I think around 5 or 10 years ago, one of the ways of looking at carbon capture was tying it into single big point sources. So, for example, coal or gas-fired power stations. Increasingly over the last 5 or so years, I think the emphasis has shifted much more towards decarbonizing big industrial processes that are difficult to decarbonize in other ways. So this is tying into lots of cluster type operations, and there are multiple examples of that around the UK and also globally. So as part of those cluster operations, I think that things are moving forward much more rapidly than they perhaps were 5 or 10 years ago.
And in a way, I suppose the more CO2 emitters that get on board, the more the industry of CCS can establish itself, and then it just the scale increases and increases. What would you say is one of the most important things about the role that you have? Is it preparing students for the future? Is it exposing them to this data?
I think in my particular case, one of the key things that I do, of course, is I train the students who come through. All of our undergraduate students come through and do things on these facilities in a hands-on way. When I'm not teaching them, we get students coming across from America, from China, from Mexico, from Malaysia, from all over South Korea. And a big part for all of those students is not just understanding the theory, but being able to apply that in a practical, hands-on way. And if we think about deploying this technology, ultimately, they're the people that will be helping to develop this technology further. So I think that's a really important aspect of what I do on these facilities.
Thank you, Dr. Colin Hale. And now that we know what CCS is, let's hear from Nigel Greatorex, the Global Business Manager of CCS within ABB's energy industries, who explains more on the technology ABB is working on within the CCS value chain.
ABB is developing a new digital technology that helps de-risk some of these CCS networks. We are taking process models and we are coupling what we call the above surface side of the network to the subsurface. And that allows you to de-risk some of the key elements of transporting CO2 from an operational perspective.
Understood. And so it's the monitoring, it's the planning, it's the digitalization of the process and looking at what happens. And then by knowing what the outcome will be when you adjust A, B, or C, you have more certainty, and more certainty means less risk.
Absolutely. And I would say the most key issue with a CCS network is availability. These CCS networks have to operate 365 days a year, 24 hours a day. So if the network is down or you have restricted injectivity, then you may have to take an emitter offline, and there'll be some form of consequential damages, should I say, as a result of having taken the emitters offline. And also these CCS networks don't operate in steady state like normal pipelines do with hydrocarbons. So that comes with significant risks as well. So it's all about availability, and it's having the right tool sets to be able to predict how that network will operate under changing conditions. And a changing condition could be an emitter goes offline. And you can only do that when you have a digital type solution made up of process models that can predict how the flows of CO2 will react under changing conditions. And that's why we're really proud in ABB to be developing and launching the world's first end-to-end digital solution for CCS networks.
Absolutely brilliant and makes total sense. Could you expand a little bit more, though, on some of the partnerships that ABB has and is working with currently in CCS?
For sure, but before I just get into the partnerships, the one thing that resonates is the need for collaboration. But if we're all to fix this issue of global warming together, then that needs collaboration. And ABB recognised this from the very start of when we started our journey looking at CCS. And we're very proud to have signed partnerships, long-term partnerships with two world-class organisations. The first organisation is a company called PACE CCS. They are the world leaders in designing these CCS networks. They're looking and specialising in what we call the above-surface side of the CCS network. And then we've also signed a long-term partnership with another world-class company called CMG, which stands for Computer Modelling Group. And they're leading the way in being able to simulate the behaviour of CO2 when you inject it into subsurface formations. Again, either saline aquifers or depleted reservoirs. So when we look at our two partners, they're both very much engaged in early phases of a project. So not only are we proud to have this expertise as part of our portfolio through partnerships, but also it gives that consistency with our partners going from design to operations across each phases of the project. We also believe is key to making CCS a success.
Absolutely. Nigel, could you give me some of the benefits that ABB's technology is addressing right now in CCS?
Yeah, I mean, I could give you multiple benefits that CCS 360 has to offer. And that's really confirmed by the market, having, discussed with so many potential customers. But the two key ones that really come to mind, I would say, and also resonate with the market is what we call transient tracking and compositional tracking.
Right. Could you expand on those a little more and how they fit into the whole CCS world?
Sure. I mean, when it comes to transient tracking, when you've got multiple emitters connected to a network, the volume of CO2 and hence the flow rates coming into that network from those emitters will vary. A great example is a combined cycle power plant. The amount of CO2 that they will produce will be defined by the demand on the power plant, and the demand will vary according to the time of day, the week, and the week of the year. And by nature, that will cause a transient. And CO2 has what we call a phased operating envelope, meaning it can come in various equations of state. And with these CCS networks, you have to operate in single phase. So when you have a transient, that could change the equation of state. The equation of state within CO2, the main two are gaseous and dense. So you need to be able to model that, especially when you've got multiple sources of CO2 coming into the network. The other point that we made was compositional tracking. CO2 will never come into a CCS network as 100% CO2. You will have other impurities within that CO2 stream. And the two types of molecules that you have is what we call polar and non-polar. With non-polar impurities, we're talking about things like oxygen, nitrogen, and hydrogen in the mole percentage range. But with polar impurities, which come in the ppm, the parts per million range. And what can actually happen is that in certain operating conditions, those polar impurities can react to induce aqueous phase liquids. And if you have too much H2O exceeding the range that you design the network against, with those polar impurities and CO2, they cause chemical reactions that can form very strong acids. And those acids will form to an extent that the corrosion rates will not be withstandable. So one of the things that most emitters will have to do is they will have to confirm the spec of the CO2 they're putting into the off-taker's network. And you'd normally do that with inline measurements like gas chromatographs. And it may well be that every emitter is complying with the CO2 spec they signed up to. But when you've got multiple sources of CO2 coming into your network, you end up with this cocktail of CO2. And that's where you can get into certain operating conditions, these chemical reactions that take place. And that's why it's really important that, you have a system that can manage and predict how those changing conditions can affect the network with either transients or compositional changes.
Understood. That makes total sense. So not only are you monitoring the phase of the CO2, so whether it's a liquid or gas, and making sure that it's in one of those phases only. And of course, that phase can change when pressure changes. So when the flow of CO2 changes, you're monitoring that, but you're also monitoring the cocktail of chemicals coming in to make sure that it stays not only within the limits per emitter, but the limits overall to make sure that what you're putting into storage isn't dangerously acidic.
Yeah, absolutely. Another area that we've been looking at through our partners with PACE is potentially chemical injection. So use certain chemicals to inject in that CO2 stream as a neutralizing agent. So that would bring down the level of NOx and SOx by neutralizing that chemical reaction that's taking place.
And all of that is only possible with the ABB systems that have been put in place.
Yes, the ABB CCS 360.
To be precise.
Absolutely.
So Nigel, to wrap up, what are you most excited about when it comes to the future of ABB's contribution in the CCS industry?
I would say what excites me most is the feedback that we're getting from the marketplace. We launched CCS 360 in March this year in London. That proceeded with being able to demonstrate it to potential customers and project developers in CERAWeek in Houston the following week. And since that period, we've had the pleasure to demonstrate the software to over 700 customers in all corners of the globe. And the uptake that we're getting in terms of acknowledging the need for a type of solution like CCS 360 is unprecedented. And it's great to be part of a new journey. I worked in oil and gas for 30 years. I thought I'd see my career out in oil and gas, but now you have the opportunity to be creative, entrepreneurial. You need to contribute towards the energy transition because let's face it, it affects every single one of us.
And it's such a fascinating mix of predicted chemistry, actual chemistry, technology, all with a sustainable lens.
Absolutely. Absolutely.
And Nigel, he spoke about two partners of ABB who are critical in their CCS work. There is PACE, who are world leaders in designing CCS networks, and CMG. And we have Anjani Kumar from CMG up next. Anjani is the Vice President of CoFlow and Professional Services. And he started by telling me exactly what it is that CMG do.
My work at CMG is basically split into two key areas. One is more on the client interfacing role. The other role is that I lead the CoFlow development and commercialization business initiative at CMG. And CoFlow is a really innovative product that has been developed in partnership with Shell and Petrobras. It is the industry's first integrated production systems modeling software that is built on the concept of multidisciplinary collaboration, data sharing, and breaking silos across disciplines.
Brilliant. So we are very much focusing on carbon capture and storage. So could you tell us a little bit more about the technology that you're using at CMG and what you're working on within the field of CCS?
CMG is a specialist in this area. Our tools, our simulation technology that we provide allows operators, engineers to analyze complex geological formations, determine storage potential, where you are going to inject, how much you are going to inject, as well as where the injected CO2 is going to end up in, say, 5, 10, 50, or even 100 years. So all these complex physics that goes in the subsurface is actually modeled in quite detail using the software solutions and the technology that we are providing.
And how does this modeling fit into the bigger picture? Because, of course, there is the modeling part of it, but then there's also the reality of making it work. And sometimes they're not the same.
Technology will play a crucial role in scaling up projects from conceptualization to implementation at an industrial level. And we need to do it faster. If you look at the time scales in which these days, if you look at any of these projects from conceptualization to implementation is anywhere from 3 to 5 years. But if we need to meet our net zero goals faster and sooner, technology is going to play a very, very key role in this, enabling operators to understand the uncertainties, complexities, and in order to design the operations safely, we need technology and the tools in the hands of users, engineers, operators to help them design these projects efficiently and faster. And that's what CMG, along with ABB, is bringing to the table.
That does not sound like an easy task, to be honest with you. So looking at the bigger picture and the CCS network operators and them achieving their net zero goals, how is CMG helping them to do that?
If you look at the solution that we have come up jointly between CMG and ABB, which is CCS 360, it's a groundbreaking product to optimize the entire life cycle of the carbon capture storage projects, all the way from the source, which is the emitters, into the network, and we are capturing the entire fluid flow inside the network, steady state, transient flow from the wellbore into the subsurface, and long-term predictability. Operators who are in the control room can actually use it live, use the live data that is being fed into this tool to make day-to-day operational decisions, look at what-if scenarios where they can do sensitivities. What happens if this goes wrong, or if this emitter goes offline, or all of a sudden we are getting impurities from one of those emitters? How to handle those situations? This tool enables those operators to operate their projects efficiently, and safer operations will lead to more projects, will help us towards the overall net zero objectives for these operators.
And how important are collaborations for CMG when it comes to CCS?
CCS is a very, very complex process, and it requires multidisciplinary specialization. There is not a single company that can holistically cover all the detailed specializations that is required within this project. So if you look at a project, there is the subsurface technology, there is flow assurance, there is facilities design, there is instrumentation, risk assessment, geomechanics, all of that complex specialization. So collaboration is a must. And if I may honestly say, is silos that is usually seen in the industry should be banished from our industry. It's we have to take a collaborative approach. And I can give you an example. If you look at the entire life cycle of a project, you have your emitters, you have your flow network, you have your wellbore, you have your subsurface reservoir, and there is specialists in each of those domains. And when a project is conceptualized and design work is done, most of these specialists work within their domain with frequent touch points where they are exchanging data. But I believe there is scope for more collaboration where all these multidisciplinary domains are working together as a team, solving these and addressing these challenges, so that we are looking at this problem holistically and coming up with a design and a solution that is robust, has minimal risk, as well as maximum chances of success when it goes operational.
So when it comes to the future of CCS, what are the trends that you would foresee? Because it is a very different place than it was 5 years ago. And I'm sure in 5 years' time, it's going to be a very different place again.
Yeah, I mean, technology keeps on evolving, and with the future is about automation, and looking at things holistically with real-time data integration as you're operating the field, with the use of AI, machine learning, and with the physics-based simulation technologies. If we bring in all these multidisciplinary domains with real-time data gathering as well as machine learning and AI, then what we could do is comfortably predict where the CO2 plume is going and what state the CO2 is in every stage of the life cycle of the project, so that we can confidently predict short-term as well as long-term storativity. So the sky is the limit, and I think the key areas is collaboration, multidisciplinary teams working together, use of data as much as possible, continuous monitoring, integrating all of that data together to make informed decision on these projects, so that our forecasts and the plan that we are providing is reliable.
And how excited are you about the future when it comes to CCS?
I'm very excited. I'm very excited, and because not only because of net zero, because we need to look at sustainable and alternate sources of energy, and most importantly, scalable source of energy that meets our energy requirement. CCS is a means to that till we transition from oil and gas. We need something to continue our oil and gas operations, but at the same time, you use the produced CO2 and get it sequestered somewhere so that we are headed towards the net zero target, but at the same time able to meet the growing energy demand for the industry. CO2 projects around the world are just getting started. The technology is able to support those initiatives, and once we leverage the potential of technology and execution, I think the combination will fast track our initiatives to net zero.
Anjani, thank you so much. This has been such a fascinating conversation. Thank you. That is it for this episode. Of course, a massive thank you, as always, to our guests, Colin, Nigel and Anjani, for their insights and expertise. And this is actually the final episode of this series, apart from, of course, the bonus episode next week, which, of course, you will listen to. And also the Process Automation Podcast is back for another season. But this time, we would like to hear from you and the topics you would like us to cover in 2025. So in the episode description, there is a form, and we would like you to fill out that form and tell us the topics you would like to hear about. And also, if you would like to be on the podcast, please get in touch via that form and tell us your domain of expertise. I'm Fran Scott, and the Process Automation Podcast is a Fresh Air production for ABB. Follow now for free from wherever you get your podcasts so you never miss an episode.